Let's do this. We are talking about Unit 4, which is going to focus on Earth systems, how the geology and other components of the Earth all flow together. And in this, we'll also be reviewing weather and a number of other things. So let's get started with plate tectonics. So just as a reminder, the Earth is layered, right? We have the solid iron nickel inner core, which is dense and also has radioactivity, which is heating the outer core, which is liquid. And then we have the mantle, which is a liquid layer of magma surrounding the core. And then on the outer level of the mantle, we have the asthenosphere, which is a fudge-like substance that the lithosphere is floating on top of. And remember, convection in the mantle powers the lithosphere, which is the very outer layer of the mantle, plus the crust is moving because of convection in the mantle. We can have the lithosphere, which is broken up into different plates, have a bunch of different plate boundaries. So new crust is formed at divergent boundaries, and you need to know that one divergent boundary in the mid-Atlantic Ocean. Then we have convergent boundaries, right? And we can have continental convergent, which results in mountains like the Himalayas, or we can have oceanic convergent, where the older oceanic goes below and forms a trench, and then you get arc islands on the other side where the mantle melts and then comes out as an arc island, a volcano on the other side. You can also have oceanic continental, where the denser oceanic goes underneath and then again melts and then comes out the other side as a volcanic mountain range. And then you can have a San Andreas fault, like where we live, where they're sliding past each other, and that is a transform boundary. Okay, so just remember that these plate movements are all powered by convection, where warm magma is rising and then cooler magma is falling, creating convection currents. And just as a reminder, whenever we have one plate going underneath the other, that's called subduction, and that results in subduction zones. And here's just a picture of a transform fault boundary. Remember that in between time, tension and pressure are building up in between the time that the plates are not slipping past each other. And then we have the good old ring of fire. And so the ring of fire is the edge of the Pacific plate, and that's where we have most of the world's volcanoes and earthquakes due to the subduction action of the Pacific plate and the transform fault that's formed at the Pacific plate and the North American plate. And then you also see there the divergent boundary, which is going through the Atlantic Ocean. Okay, so let's talk soil, right? So remember that soil is important. It's got a lot of job. It filters water. It recycles nutrients. It provides habitat for organisms, provides as a means for plant growth. And remember that there's main parts of soil. Three main particles are sand, silt, and clay. And then humus is that organic content in the soil. So more compost means more humus. And then there's a bunch of nutrients in soil as well as water, air, and living organisms. Soil forms through weathering, which is when rocks become smaller. There's physical, biological, and chemical weathering, which we talked about. And then also soil can become detached and move on the earth, and that is called erosion. So make sure you know the difference between weathering and erosion. Soil over time gets weathered more and more, and so it starts as just kind of bare rock. That bare rock is weathered, and then more organic material is added to it, and over time we get more humus in the soil, and the weathered rock from down below breaks up and the topsoil becomes thicker. Speaking of topsoil, let's go through our horizons here. So we got the O horizon, which is the organic material, the A horizon, which is your topsoil, right? This is where most of the biological activity is, right? This is the money layer. The O horizon is just exclusively organic material. Then we have our B horizon, our subsoil. It contains some nutrients, but mostly just minerals from the weathered rock. And then C horizon is our least weathered rock. And then below that would be the bedrock, which is the non-weathered rock. Several things can result in soil degradation, right? And so if we over-till soil, or if we disturb soil through construction activities and it's eroded off, we can lose topsoil, and this can result in desertification. Remember that word? And then also we can over-compact soil, which makes it less able to hold moisture. We can also deplete soil from nutrients, especially if we're doing things like monocropping, growing the same crop over and over again. And here's an example FRQ on soil. So there's a lot of things that we can say about soil. We did some soil labs. We measured soil. We can talk about soil texture, like the percentage of sand, silt, and clay relative to each other. Remember that sand is the most porous, right? It's the amount of space a soil has. And we can also look at the permeability of soil as well. But let's go ahead and remind ourselves this soil texture chart. So when you're doing your soil texture chart, I always just do the percent sand and percent clay. The percent sand lines go up and to the left. The percent clay lines go across. Percent sand lines up and to the left, percent clay lines up. The silt lines are kind of from the top right down to the bottom. And so just make sure you're paying careful attention to how you're reading those axes. And you can go ahead and look at this sample question if you want to pause the video right here. Okay, so porosity again is the space within soil, and more sand equals more porous, and then permeability is how easily water drains through the soil. The highest water holding capacity, right? That is going to be clay, because clay has a higher capacity to hold water. It also has let me come back to that. But anyways, the highest water holding capacity is clay. Okay, so we're talking about soil fertility. We can do a number of chemical tests. We can test soil for nitrogen, phosphorus, potassium, calcium, sodium, but NPK, nitrogen, nitrates, phosphorus, phosphates, and potassium K. Those are the big three. We can also measure how much organic matter soil is holding. We can measure the pH of soil, and we can measure how much water it holds and how fast water moves through it. And again, if you were asked to identify some soil tests here, these are all different soil tests you could do. And we did all of these tests. The atmosphere. Okay, so we know the atmosphere is mostly nitrogen, about 78%, followed by oxygen, 21%, and then argon, followed by water vapor. And then CO2 is just about 400 parts per million, which is 0.04%. So relatively not as much, despite the fact that we talk about it a lot because it's driving climate change. The troposphere is the layer closest to the Earth. That's where weather occurs, and that's where the greenhouse gas effect occurs. Then we have the stratosphere, which is where the helpful ozone is found in the ozone layer. Then the mesosphere above that, the thermosphere, and finally, the last layer of the Earth is where the atmosphere merges with space, and that's called the exosphere, sometimes the ionosphere. And there's a temperature gradient here, and most likely you'd be given a graph of this and asked to interpret it, but the direction that the temperature goes as you move further away from Earth changes with every layer that you're in. Okay, and let's talk wind. All right, so we have large scale convection. This is where you have these convection cells that vary each 30 degrees latitude. So at the equator, you have warm, moist air rising, and it rises, it cools, it drops its water. The air continues to rise and then becomes denser, and then it falls at 30 north, 30 south, creating deserts at 30 north and 30 south. That is called a Hadley cell. We also have surface wind patterns caused by the rotation of the Earth. The Coriolis effect causes clockwise rotation of wind in the northern hemisphere and counterclockwise rotation of wind in the southern hemisphere. And this leads to ocean currents, which drive water in certain directions, which we'll get to. That's caused by the spinning of the Earth. And so when you take these combination of like this large scale convection, such as the Hadley cells and the Coriolis effect, we get these prevailing winds. And the most important ones to know are where we have the trade winds, which the trade winds are blowing from the east to the west, and they meet in the middle where there are the doldrums, which is essentially where they cancel each other out. And then you have the opposite thing happening at every other So above the trade winds, then you have the westerlies, and above that you have the easterlies. Watersheds. This is an area of land where water all drains to the same location. We've talked quite a bit about watersheds, okay? And you can determine it by the ridge of the mountains. And there's a bunch of different ways that you can classify watersheds, such as their vegetation, their slope, their soil permeability. And humans impact watersheds through a number of activities, which we have and we'll remind you to talk about. One important watershed we didn't really spend time on, though, is one on the East Coast, and it is the Chesapeake Bay watershed. And at the drainage area of the Chesapeake Bay watershed, it's an estuary, and that means the salt water and the fresh water from the ocean and from the land, that would be the fresh water, obviously, are meeting right there. And this is an example of a wetland, which provides a number of ecosystem services, such as tourism, water filtration, recreation, habitat for food and sources, storm protection. These are all examples of the ecosystem services of a wetland. The Chesapeake Bay, just continuing with this as a case study, has been heavily polluted, mostly through farm runoff, mostly through chicken farms. And this has led to the eutrophication of the Chesapeake Bay. And just remember, the eutrophication is where you have excess nutrients run into the water, right? And excess nitrates or phosphates cause an algae bloom. The algae die, and they also cause a decrease in sunlight to the bottom. The bacteria decompose the algae. You end up with a hypoxic or a dead zone. And this mostly comes, this excess nitrogen and phosphorus, either from CAFOs, as it is mostly the case with the Chesapeake Bay watershed. We have animal waste running off, or it could be discharged from sewage plants, or very commonly just excess fertilizer from farms and lawns. Other things that can affect the water quality of a watershed are things like clear cutting. Clear cutting is where you cut down an entire forest. That leads to more soil erosion and also increased temperature, which means less oxygen in the streams nearby because there is less shade. Higher turbidity, right, too, because you're going to have more sediment in the water. And so there's a lot of solutions to watershed pollutants. Obviously, you could have more buffers, riparian buffers on the edges. You could have more water infiltrate and less water run off, and that would certainly improve water quality. And we'll get into some of those other improvements shortly. Okay, let's get to solar radiation. Remember that insolation is the amount of incoming solar radiation that is absorbed by the Earth. And the equator has the highest rate of insolation because the sunlight is hitting at a directer angle and it has to travel through less atmosphere than at the poles. And that's why we have more incoming solar radiation or solar intensity at the equator than at the poles. And remember, and this is just another example of that, also the rays are literally farther apart. And that's why when they're hitting more directly, you end up with more solar radiation. Should be able to look at a diagram like this as we've done and interpret what season it is. Remember, it's the tilt of the Earth on its axis that causes the seasons. And when the northern hemisphere is pointing towards the sun, it's summer in the northern hemisphere and winter in the southern hemisphere, and vice versa is true. Albedo, this is the idea that Earth reflects some of sun's incoming solar energy, and higher albedo means more reflection. A mirror has a very high albedo, ice has a very high albedo, and surfaces that are darker have less albedo. And so that's why ice literally keeps the Earth cool by reflecting the sun's radiation. When that ice melts, we get more solar radiation absorbed and the Earth warms up at a faster rate. And so ice melting is an example of a positive feedback cycle in climate change, right? And so we can look at little areas with a lot of black, such as pavement, asphalt roofs. These are areas that are going to be warmer, and obviously that's typically cities. And so you can have the urban heat island effect where we have cities and they're absorbing more radiation and giving that off as infrared radiation, contributing to warmer areas where there are cities. We can also look at Earth's geography, right? There are some microclimatic effects, right? So obviously oceans help regulate temperatures, but also so do topographic features. One of those topographic features is the rain shadow effect, which is where the idea where you have a tall mountain and you have moist air being lifted up the mountain, and that moist air cools down, and now remember, cold air holds less water, and so that water then rains out of the clouds, falls on the other side as dry, and you get a desert on the other side. That's the rain shadow effect. The Himalayas and the Sierra Nevada mountains are a really good example of the rain shadow effect. We also can have weather influenced by wind patterns, and I will just go ahead and get to one of those really important ones, which is El Nino and La Nina, which is where we have a change in the wind patterns. And so if you remember, so because of surface currents, we get these ocean gyres, right? And that's all due to the Coriolis effect and other types of ocean circulation, which we'll remind ourselves of in a little bit here. But one of those things that can be caused is an upwelling, which is right off our coast, right? Where we have water from deep, cool, deep, dense water coming up because of these ocean currents are pulling water away from the edge of the continents. And so water comes up, and this water is cold, nutrient rich, oxygen rich, and causes areas of high productivity. So another example of an ocean current that's not a surface current but contributes to this is thermohaline circulation, which this is a density driven current, which if you remember, we looked at the visual of this, and you have dense salty water falling at number 2 right there, which is driving this current, and that current is going to slow down as Greenland melts and that water becomes less salty. So during an El Nino or an ENSO pattern, right, this is where the trade winds weaken, and so the upwelling slows down, and so the water off of our coast, which is the Eastern Pacific, becomes a little bit warmer, and that means fisheries have less productivity, but it also means you have more rain in our region. The opposite is happening on the other side of the Pacific. La Nina is the opposite. When the trade winds strengthen and the upwelling strengthen, and our ocean gets actually a little bit colder, and we end up with because the upwelling increases, and we end up with more productive fisheries and drought on the land surfaces. And this is just a summary slide of what I just said if you want to pause and write some of that down. Okay. And again, another summary slide of the effects of El Nino and La Nina. And that is it for Unit 4. Thank you all for hanging in, and I hope that was helpful.